All right, guys, welcome to another episode of CUDA Education. Today, we are going to cover the topic of procedural ray traced geometry. Um, and we're just going to do a quick overview of the algorithm that was provided as part of the samples. So all of these are samples that are freely available on the internet. Um, and if you want to be able to run these samples on your machine, you need to get tutorial number 1 and tutorial number 15. So I said 13 previously, but it's actually tutorial 15. So tutorial number 1 is to install the Vulkan API on your Windows-based machine. Tutorial number 15 is to install the these examples here. Okay, so we're on the ray tracing intersection algorithm. Um, the actual code that I have here on GitHub, because the author of this algorithm actually he updates the code periodically. So the actual code that I have here that I might be reviewing, it might be slightly different from the latest code that you see on GitHub. But there's a feature on GitHub where you could look at the previous versions of the code, right? So if you have older code, you could toggle an option to see the older version that maybe syncs up with what I have, because I installed this a while back. So maybe what you see might be slightly different. But if you Google ray tracing intersection Sascha Willems, you will see you will see this algorithm. And I'm just going through the process of learning learning ray tracing, right? And I'm taking you along for the ride. So I'm coming to this whole situation as an amateur myself, and I'm taking you guys along for the ride, because it's all the rave and all that stuff. If you can see here, you notice that all of these examples here are ray tracing examples. The rest of the examples are just normal computer graphics examples. You're not necessarily dealing with ray tracing. You're just dealing with straight computer graphics and the Vulkan API. But these examples here are the ray tracing examples. If you install these, if you install this solution, these examples, you will still be able to run the non-ray tracing stuff if you have a GPU that's not ray tracing capable. So I know for NVIDIA GPUs, it's the RTX line, right? So if you have like the GeForce line or what have you, you won't be able to run the ray tracing examples, but you'll be able to pretty much run everything else, right? So just be mindful that if your GPU is not ray tracing capable, you won't be able to run the ray tracing examples, but you'll be able to run everything else. Okay, so this ray intersection example, basically what it does is I will show you, it generates a bunch of spheres, okay? And it does it using a thing called procedural geometry, okay? And basically, as you can see, and there's like a light source and stuff, and the light source moves and all this stuff, right? And you could zoom in and out, all that stuff, okay? So procedural ray traced geometry. So what that means is that we're not using a 3D model. We're not using triangles. We're not passing some sort of model that was created by a third party into the algorithm in order to create the spheres. The spheres are being created mathematically, right? And because it's being created mathematically, it means that you have, it's sort of being created organically in the algorithm. So you have, so we'll say that um, it's done organically, it's done mathematically. You're not passing in any kind of model or mesh or anything, which means you don't have memory burdens, you don't have data burdens, you don't really have like processing burdens as such, because it's all done organically. So you see the number of circles that were in the application when I ran it. Obviously you can maximize the number of circles in the application with minimal cost, compute cost and stuff, frame rate cost and all that stuff, because basically it's all being done mathematically, right? Um, so that is why procedural geometry is a thing. Um, it's usually used for like terrains, for like clouds, in video games, like when you're moving through a 3D world, and you need to pop up trees and things of that. Well, I guess trees, I don't know if you can really do that mathematically, but like leaves maybe or something like that. Um, Terrains, cityscapes, crowds, what I think called fractals, all that stuff. It's procedural geometry. We are concerned with the ray tracing piece, so it's called procedural geometry. But we are concerned, not only with procedural geometry, but the ray traced portion of it, right? Because of course, it's one of the ray tracing algorithms in the sample, and we're trying to see how this is done in a ray traced situation. My understanding of what that means is that you have the sphere, and then you have rays being shot into the scene. And then when rays are shot into the scene, the rays hit what is called an axis aligned bounding box. Okay. And basically what it is, it's like a 3D square or a 3D box, square rectangle, like a 3D square, right? That basically surrounds the sphere, right? So when the rays enter the scene, this is a very rudimentary amateur explanation, but when the rays traverse the scene, it's going to hit these axis aligned bounding boxes, and when you hit those boxes, then you get a reflection, and that's how you're able to see the fact that there are spheres in that particular location. So all those spheres basically is surrounded by an axis aligned bounding box, and that's how the rays are able to detect that spheres are there, right? That's my very rudimentary explanation of the matter. Instead of passing actual geometry, this sample only passes bounding boxes and sphere descriptions. The bounding boxes are used for the ray traversal, and the sphere intersections are done within the intersection shader. I think just the best way to sort of process all this stuff is to just walk through the code, pick up what we understand, and learn as we go. So let's just do that. Let's just walk through the code, right? We're looking at 600 lines of code. All right. A lot of the stuff is just standard issue boilerplate stuff, because you know how Vulkan does it. A lot of it is encapsulated with other functions too, so that kind of helps us. But yeah, let's just go through it. So we start with the base class, Vulkan example, Vulkan ray tracing sample. We have acceleration structure, bottom level acceleration structure, top level acceleration structure. You guys should know by now, bottom level is geometry based stuff, even though here we're not necessarily, we're doing it with mathematical equations, not necessarily like triangles and meshes and models. And then top level acceleration structure is instance based stuff. We have a vector of shader groups. We have a regen, a miss shader, a hit shader, and that's all part of the shader binding table. We have the uniform data. This is usually dealing with the camera, right? So just basically, our view of how we see the, what side and whatever we see the spheres and stuff. Pipeline layout, descriptor set layout. We've done this a million times already. We have a sphere, we have a center, radius, and the color, right? And then we have AABB. So this is axis aligned bounded boxes, right? Axis aligned bounding boxes. So for example, if you go to Google Images and you type in axis aligned bounding boxes or AABB, whichever one you prefer, or both, and then you type in min max, you're going to see how the bounding boxes are defined. So let's say you have a 3D square. So you have 1, 2, 3, 4. So this is like the front facing of the square, and then you have 1, 2, 3, 4 on the back facing of the sphere, and then the lower rear left point is the min, and the upper front right point is the max. And that is how the 3D square is defined, right? The 3D bounding box. So remember, it's a 3D square, right? And then you have the rear left and the upper right. That's how you define what the axis aligned bounding box is. You could go to Google Images, type in AABB, min-max, computer graphics, or axis aligned bounding box, min-max, whatever you want to do, and you will see that you get a min, you have two parameters, the min and the max, and that defines the entirety of that box. And then if rays hit that box, then we register an intersection with that. Now, I'm going to assume, right, that the sphere is inside of those boxes, right? So that's how we register that something that the rays have hit. There's a reflection, and then the reflection comes back to our eyes or to the camera, and that's how we know that a sphere is there, right? Very rudimentary explanation of what's going on. Spheres buffer, AABS buffer, AABS count. So then we get into just camera stuff and the title of the algorithm. We have destructor stuff. Okay, we'll be using two buffers to describe the procedural geometry. So when I see buffer, I generally think of memory and like storage space. That's just my personal view of when I see the word buffer. A buffer with randomly generated sphere descriptions, center, radius, material. That'll be passed to the ray tracing shaders as a shader storage buffer object. So we have a vector sphere. We randomly generate sphere description. So of course a sphere is defined by its center, its radius, and whatever material is being used. Yeah. And then we iterate for the number of spheres, right? So let's just run our algorithm, and we see we have a whole bunch of spheres here, right? Okay. And we could zoom in, right? And we could zoom out. And notice that like we don't see any kind of triangle, mesh, any kind of thing. It's just a clean circle with no like triangles that are trying to simulate a sphere, right? It's just clean and organic, nothing like that, right? Okay, so we see a whole bunch of spheres here, right? So just as a sanity check, let's just, instead of doing the 4 for 1024 spheres, let's just do it for 1. And you're going to see that we just have this 1 sphere, right? And I guess the position of it is randomly generated, but we see we have our 1 sphere, okay? Now let's do 10, okay? So we're going to do 10 spheres, and then when we run it, we have our randomly generated 10 spheres, right? Notice that the color and the locations and stuff is different, right? That's basically all this is, right? If we do 100, we get this much, right? For whatever it's worth. Obviously, I'm not going to sit here and count that it's 100, but I'm just going to assume that it's somewhere along those lines, right? Okay. So we have our sphere. We randomly generate location, all of that stuff, and we push the spheres in, right? So we generate them and what have you. A buffer with the axis-aligned bounding boxes of our sphere, which is used during the ray tracing traversal for hit detection. A buffer with the axis-aligned bounding boxes of our sphere, which is used during the ray tracing traversal for hit detection. So we have axis-aligned bounding box, a vector, and then we create, I guess this is like you're creating the bounding box. Let's see. So we're going to comment out this guy right here and see what the hell happens. And we get a crash. Hopefully you're still there though. Are you still there? Yes, you're still there. Okay. So we can't just comment it out. Now let's try to, we'll define it, but we don't put anything in it. Let's see if that works. All right, so we have to define it because we just have to. But notice that we don't see anything, right? And like I said, I'm being consistent. See, I'm not lying. I'm not lying to anyone. I'm not in public office. Okay? As we surmise, if we don't have the bounding boxes, we don't get any intersections and we don't get we can't detect anything. If we do have the axis-aligned bounding boxes, then we are able to see everything. You see? So that's our little lesson to know that a buffer with the axis-aligned bounding boxes of our sphere, which is used during the ray tracing traversal for hit detection. So we're trying to make sure that we see the spheres, right? All right. I want to just do something real quick. So let's say we keep everything as is, but then we don't update the count. So I think the count was initialized to 0, right? So let's keep the count to 0. If the count is 0, our application doesn't crash. But again, if the count is 0, we don't have any axis-aligned bounding boxes, and therefore we don't see any spheres, right? So that matches up with what we expect, right? So we're sort of on a good path, right? So we get our spheres back. All right, so we're learning stuff. Copy the buffer to the device for performance reasons. Okay, so when you say the word device, we know that we're talking about the GPU, right? So in the world of computer graphics, at least in the Windows world, we have the host, which is your laptop or your computer, your desktop, whatever it is, the CPU side. And then we have our GPU, which is the device. So there's host, CPU side, your laptop, your computer, and then device, which is the GPU. You know that big giant thing that you spend a whole lot of money on to buy the GPU? Yeah, that's the device. Copy the buffer to the device for performance reasons. So this is a memory operation. Anytime you see the word staging buffer, you know, like you're trying to transfer stuff from the host side into the GPU, into the device, into the GPU. Because if the buffer, I'm going to assume you're talking about access aligned bounding boxes, if they're in the GPU, generally speaking, you can access the data faster. It runs better. You don't have to deal with the pipeline between the host and the device to display stuff. Yeah, not gonna get into all of this right here, but these are all kind of stuff that you do for the staging buffer. So we're moving stuff over, Vulkan device, staging buffer, all that good stuff. Axis aligned bounding boxes. We're doing the same thing here. Right, so we're moving spheres, I guess, and we're moving the axis aligned bounding boxes, right? So, I mean, I guess here we could say that these are two separate things, you know, so it's not like everything is encapsulated into one. You have the spheres and you have the axis aligned bounding boxes, okay? And then I guess once you're done with the with moving stuff over, you could destroy the staging buffer, okay? We practice good housekeeping here at CUDA Education, and we destroy the staging buffer, okay? We don't just leave stuff hanging even though it's not being used. And I hope you guys that are going through this with me, I hope your house and your room and everything is clean, right? If you're going to be a good programmer, you have to program in clean environs, okay? So make sure you do some vacuuming, make sure you do some cleaning. You understand? Make sure everything is organized around you, not just organized on your file system and on your monitor. You got to make sure your environment is organized. See, we're organized here. We destroy things after we're done using them. You have all these destructors here that destroys things. You know what I mean? It's just good advice for life. Okay? All right. So create the bottom level acceleration structure only containing axis aligned bounding boxes for procedural geometry. Okay, so remember, like we have talked in the whiteboard edition, in my simple overview of ray tracing, that we have this bottom level acceleration structure which normally hosts the triangles and the geometry of whatever it is you're trying to see in your application. Okay. Well, in this particular case, remember, we don't have any geometry or meshes or anything or triangles or anything that we're passing into our application. We just have these axis aligned bounding boxes which act as our dummy intersection detectors, right? So I guess for the bottom level acceleration structure in this particular case, because we are dealing with ray tracing, so we're going to get a bottom level acceleration structure, but because we're dealing with procedural geometry, we use these axis aligned bounding boxes as our quote unquote geometry, right? As our quote unquote mesh or whatever. But this is all generated internally, right? We're not we don't have any matrix of vertices or anything that we generated. It's all random generator stuff, whatever. Yeah, right. So the bounding boxes act as our quote unquote geometry. So instead of providing actual geometry, example triangles, we only provide the axis aligned bounding boxes, AABBs, of the spheres. The data for the actual spheres is passed elsewhere as a shader storage buffer object. We're not going to get into that right now, but just know that you know, we're dealing with the access aligned bounding boxes, right? And that's all this is. This is like memory stuff, right? Get size info. Right. Okay, so we're gonna get size info and stuff. Yeah, you know how Vulkan does, guys. Come on, you know how Vulkan. You know, it's you know how it does, right? So get acceleration structure build sizes KHR. Um, it's retrieve the required size for an acceleration structure, right? All right, the third parameter is the build info, right? So this guy, primitive counts. So you have device, build type, build info, primitive counts, and p size info, right? So those are the parameters for this guy. All right, so now we're creating the acceleration structure. Yeah. So we have a bottom level acceleration structure, right? Okay, so create a small scratch buffer used during build of the bottom level acceleration structure. Don't really have much insight into this right now, but he uses a couple times he uses a scratch buffer concept. I guess we'll get into that at a later point. Build the acceleration structure on the device via a one-time command buffer submission. Some implementations may support acceleration structure building on the host, but we prefer device builds. All right, I guess we prefer device builds, guys. All right, so you know my rule. Anytime you see a lowercase vk function, anytime you see a lowercase vk function, you know like it's serious business. Like it's no longer set up anymore. Like we're actually in the real deal Holyfield, okay? We're not messing around. So this is build an acceleration structure. So we do all of this stuff up here just to get to this guy, right? So where do you use the scratch buffer? All right, scratch buffer. Okay, scratch buffer. Okay, all right. I don't want to dive into this particular thing, but yeah, when you see a lowercase vk, you know we're actually, you know, we had to do a lot of work to get this going, this going, this going, this going. So well, at least this all this stuff right here, right? So that's the nature of Vulkan, is that it's a whole bunch of text and things you got to declare so that you get this one grand finale of a lower vk's function that's supposed to do everything you asked it to do because you set up everything before. That's the blessing and the curse of Vulkan. The blessing is that you have control over everything. The curse is that you got to declare everything. And trust me, if anything is out of line here, the whole thing blows up, right? So it's a blessing and a curse. You either want the control and the detail and have to declare everything and make sure everything is lined up, or you want no control and no detail, and it's like a little bit of text, but then you don't have any control or any detail, right? So that is the big jump from OpenGL to Vulkan. So OpenGL was very easy, surface level stuff. Things are done for you. It's like one function that does everything for you, but you have no control over how things are done. Whereas Vulkan is everything is explicit. You got to do everything yourself, but you have control, which means you can optimize things and you could take advantage of hardware more, you know, insidiously, or you know what I mean. You could get it to do exactly what you want and not have to worry about unnecessary overhead because you got to type all this stuff out. All right, so top level acceleration structure contains the scene's object instances. So create top level acceleration structure. Okay, before we even go there, what I want to do is let's see if what if I just disable the what if I just disable the bottom level acceleration structure? Will everything still work or will it crash? All right, well, everything still works, but I don't get anything, right? That makes sense. I don't have any axis aligned bounding boxes, so I'm not going to see anything. If I bring back in my bottom level acceleration structure, I'm going to see stuff. Okay? Now, before we get into top level, remember top level is now the instances. So it's all those instances of the circle that you see. So let's look for the lowercase vk. All right, so let's try and do this. So remember we got our lowercase vk here. We also had a lowercase vk here, but it's a get function. I don't care about getting nothing. I want to disable the top level acceleration structure, right? So I just want to see what happens and hopefully it doesn't crash, right? So, okay, application doesn't crash, but I don't see anything. Again, I have the bounding boxes, but I don't have the instances. So I'm not going to see anything, okay? So that's what this is. All right, so when we put back the top level acceleration structure, we get back our spheres. All right, so we kind of see what the top level is about. Okay, so we have our transform matrix. I'm not really sure what is this like for the whole blob. All right, let's just do something here and see what happens. So if we mess with the transform matrix, all right, I'm zooming all the way out, I'm zooming all the way in, I don't get anything. All right, let's just do one. I don't know what that means. All right, guys, you see how it's kind of like split? I don't know what that means. I don't know what that means. I haven't, if you guys have any suggestions as to why this is doing that, I don't know. Is it transforming the bounding box? What is it transforming? It's transforming the bounding box so you only see a part of the sphere or something? Ugh. Is that what it's transforming? But like when you move it over, like it kind of does a visual trick. Listen, I invented something here. I invented a new thing. I don't know. Pixar, you watching? No, I'm just playing. Um, I guess it's tinkering with the bounding box, so like you wouldn't see, you only see a portion of things. Um, you see, but then when you turn it, so I don't know, guys. You guys tell me what you think. But that's the transform matrix is I guess playing around with. I don't know. I don't know. The instance is playing around with, well, right. The bottom level acceleration structure is a bounding box. So the top level, you're playing around. You're transforming the instance. I don't know what it's doing. You're transforming the instance. I don't know. That's homework for you guys. Yes, there's homework here. All right, so then we have our acceleration structure instance. Buffer for instance data. Buffer for instance data. I don't know. This is a similar stuff of what we saw before. Um, so it's similar things that we saw for the bottom level. And basically, it's all that stuff is done for this guy right here, right? So all of this right here is done just for this, right? The lowercase vk function. All right. All right. Create shader binding tables that bind the programs and top level acceleration structure. Regen, miss, hit plus intersection. So create shader binding tables. You know, we've played around with shader binding tables. Obviously, this is, you're generating rays into your scene, so you could test stuff and see what's going on. So you're generating a ray into a scene. This is what happens if you miss, and this is what happens when you get a hit or intersection, right? Create the descriptor sets used for the ray tracing dispatch. We pass the sphere descriptions as shader storage buffer, so the ray tracing shaders can source properties from it. Memory operations. Okay, binding 0 is the top level acceleration structure. Binding 1 is ray tracing result image. Binding 2 is uniform data, and binding 3 is spheres buffer. VK update descriptor sets. So this I will need to invest more time. I know we're dealing with a lot of memory operations and moving stuff around and things of that nature. Descriptor sets are largely deals with like describing what's in memory, making it accessible to everyone. You know, making it being, it's almost like you have a USB stick and you're making sure you label the USB stick so you know exactly what is on the USB stick, right? Yeah. And we have our lowercase vk here, right? So we're updating, create our ray tracing pipeline. All right, guys, you know, we've seen this before. Layout bindings, binding 0 is acceleration structure, 1 is storage image, 2 is uniform buffer, 3 is spheres buffer. Yeah, I'll have to spend more time in diving into this stuff. Set up ray tracing shader groups, ray generation group. So we have our ray gen group, which is this guy right here, right? So let's just, we have our ray gen group, our miss group, intersection, closest hit, and our intersection. So let's look at the ray gen. I'm not even gonna dive into this right now. But this is our ray gen shader. This is our miss shader. Okay, I mean, one thing I do know with the miss shader, right? So if rays traverse the scene and there's no hit, you basically issue a color. So I guess this color is blue. If I change the value, and I think I have to rebuild. I have to rebuild the whole thing because this is like a separate file. So I have to rebuild the whole thing in order for the change to register. Right? So when I rebuild the whole thing, I was hoping that the sky model would be a different color. Right? I don't know. Yeah, I was hoping the sky model would be a different color, but it's not. I don't know. I don't know why exactly I'm not able to get this to register. Right, so that's our miss. Closest hit is this stuff, which yeah. And then we have our hit intersection, right, which is this stuff here. Right. So basically, I know that if I comment out the intersection, right, I don't get anything, right? If I comment out the intersection shader, I don't get anything because there's no instructions for what happens when a hit is registered, right? Let's see for them. So we have a blue background normally, right?